Okay, it is calculus time, and we're up to lesson 25. Any questions before we start this lesson? So we've already seen what is called the indefinite integral. Which is the same as the antiderivative. So, and the notation is just this elongated s times some function like x squared plus 3x plus 5. And this means find a function whose derivative is equal to this. And you can check that it's 1/3 x cubed plus 3/2 x squared plus 5x plus any constant c. So c is an arbitrary constant. And that's what it is. And in Math 176, you will spend a lot of time learning techniques of integration. But if you're learning Maple in Math 156, you will have seen that Maple can integrate everything very easily. It's quite amazing. So we'll come back to this, but I want to look at a different problem, which is a kind of a geometrical problem, which is finding the area under a curve. So, for example, suppose you take a semicircle. So this is a non-negative function. Let's say its radius is r. So this is minus r, r, r. And we want to know what the area is. And of course, you learn that in school at a very early age, namely the area of a circle is pi r squared, and a semicircle is half of that, so you divide it by 2. So that's the area of the semicircle. But suppose you have something different. Suppose you have, let's say, this is a part of a parabola. Let's say this is some number, I can call it r, it doesn't matter. This is the parabola y equals r minus x squared. So when x is 0, this is r, and y is 0 at square root of r and minus square root of r. And we can ask, what is the area of this parabolic region? And we didn't learn how to do that in elementary school or junior high school or high school, or probably not in calculus yet. But it's a very reasonable problem, and we like to find the answer. And the answer comes from what is called, so this is the answer to the geometrical problem, is what is called the definite integral. The indefinite integral, that's just the antiderivative of a function. But the definite integral isn't a function. It gives you a number. And one way to interpret that number is the area under a curve. And there is a simple procedure that we could attempt to try and find the area if we didn't know anything at all. And that's the following. So go back and look at a simple example. Well, let me use a different function just so that I can use an example that's in the book. Suppose we have the function f of x equals the square root of x. So so it's 0 at 0, it's 1 at 1, and the square root of 4 is 2. So this function sort of goes up like that. And let's say for some number, we want to find the area for, let's say, x between 0, well, maybe even just up to 1. X between 0 and 1, and y between 0 and the square root of x. So that's just the area that I'm going to shade in red over here. So in the text, they give an example of how you could solve a problem like this. And let me continue with the example in the text. I just want to draw a better picture. So let's say this is 0, 1, 1. And we're looking at the function f of x equal the square root of x for x between 0 and 1. So it looks like that. And one way to find the area might be the following. Suppose we divide this interval from 0 and 1 up into pieces. And for each of these little pieces, we could draw perpendicular lines and maybe build this. Look at this rectangle. So this little rectangle, it's bigger than the area under the curve from here to here, but it's close. And you might think if you divide this interval up into a large number of pieces, not necessarily all of the same widths, if you could calculate the areas of these rectangles and add them up, right, you have all these rectangles, you would get an approximation to the area under the curve. And that is what we're going to do. So the idea of the integral is to approximate the area under the curve by a sum of rectangles. And let's see. Actually, so let me go back to an easier example in the text. So in the text, let's look at example. This is a good example. Actually, maybe I'll do this example, but now let me go back and do an easier example. So in the text, I want to look at example 3 in section 5.2. So in this case, we're looking at the function f of x equals minus x squared plus 5. So this is a parabola that's coming down. And when x is 0, it has the value 5. When x is 1, it has the value 4. And when x is 2, it has the value 1. So this region looks like this. And what we're going to do is divide this interval up, the interval from 0 to 2, into 5 pieces. So each of them is going to be a length 2/5, 2/5, 4/5, 6/5, 8/5, 10/5 equals 2. I divide this interval up into 5 pieces, and over each of these pieces I build a rectangle. And so let's see, suppose this is one of these pieces. The part under the curve looks like that. And I could build a rectangle where I take, for example, the right-hand endpoint of the interval and draw this horizontal line. So let me try and draw a better picture of this. This is 0, 2. This is the function f of x equals minus x squared plus 5, or 5 minus x squared. So this is 5. And I'm taking the interval from 0 to 2 and dividing it up into 5 intervals of the same length, 2/5, 4/5, 6/5, 8/5. So here is one of those rectangles. And I could choose, for example, for each of these rectangles, the right-hand endpoint. And use that as the height of my rectangle. For example, when x is 8/5, f of 8/5 is equal to minus 8/5 squared plus 5. That's 5 minus 64 over 25. Let's see, 5 times, that's 125 minus 64 over 25. Or what is that? 161 over 25. Yeah. So, for example, this red rectangle has area 61 over 25. And I could construct the areas of all 5 of these rectangles. And, sorry, that's the height. So the area of this red rectangle, the area of a rectangle is the height times the base. The height is 61 over 25, and each base is 2/5. That's equal to f at 8/5 times 2/5. So if I add up the areas of these rectangles, we use what is called sigma notation, because this is a capital Greek letter sigma. And if you have some notation that looks like, for example, summation I goes from 1 to 5, a sub I, that means you have some numbers, A1, A2, A3, A4, and A5, and you're adding them up. So here, when we're looking at this part of the curve of the parabola minus x squared plus 5 between 0 and 2, each of these rectangles, so if I take the point, each of these points is like 2i over 5, where I is between 0 and 1. Sorry, I is between 0 and 5. 0, 2/5, 4/5, 6/5, 8/5, 10/5. So if I take summation, I goes from 1 up to 5, f of x sub f of, what is this point? This is going to be denominator is 5, 2i is the numerator. 2, 4, 6, 8, 10 times the base 2/5. This expression gives us the sum of the areas of these 5 rectangles that is approximately the area under the curve. Right? So this is summation I goes from 1 to 5. F of 2 over I over 5 is minus 2i over 5 squared plus 5 times 2/5. And this is just something you can calculate. I mean, I can factor out the 2/5. And this is when I is equal to 1, this is minus 2/5 squared plus 5. And then minus 4/5 squared plus 5, and so forth. This is just some big expression, but there are only 5 terms. You can take out your calculator and compute it, and you get an answer for it. I mean, the text computes the answer, gets 162 over 25, which is approximately 6.48. So if you wanted to find the area under the parabola from 0 to 2, a first step would be to divide this interval from 0 to 2 into 5 equal pieces, draw the vertical lines at each piece, use the right-hand endpoint of each subinterval to draw the horizontal line, and that gives you 5 rectangles, which approximately equal the area under the curve. That's the whole idea of that. All right. Alternatively, at each point, you could have taken the left-hand endpoint. In that case, you would have gotten a bigger series of rectangles. You would get another approximation to the area, but that would be like an upper bound. This gives you like a lower approximation. Choosing the left-hand endpoints would give you a upper approximation. But that's the whole idea, which goes back at least to the Greeks, about how to figure out approximately what an area is. You take this area, which has a curved boundary, this is hard to understand, and you approximate it by rectangles, which are easy to understand. And you know what a rectangle is. You know the area of a rectangle is just the base times the height. And if you do it very carefully and you have more and more subdivisions, you can actually compute an area. So let's look at another important example. So this one I'll actually compute exactly. This is example 4 in section 5.2. So in this example, we're looking at the traditional parabola, f of x equals x squared, for x between 0 and 2. Just one second. So it's the parabola. Looks like that. And we want to calculate the area under the curve. So what we can do is, this is our first step, divide the interval from 0 to 2 into n pieces, and it's sometimes easier just to make them n equal pieces. And if you divide length n into n equal pieces, each is going to have length 2 over n. So your interval from 0 to 2 will look like 2 over n, 4 over n, 6 over n, and so forth, up to 2, which is 2 n over n. Right? Each of these intervals is of the form 2i over n, where I goes from 0 up to n. Right? So all we're doing is taking this interval and dividing it up into n equal pieces. And for each of these pieces, these are two successive points, we're going to draw the perpendicular lines. And let's say we use the left-hand endpoint to draw a line parallel to the x-axis, so we actually have a rectangle here. So let's just sort of blow this up a little bit. If you have 2i over n, then the previous point of subdivision of the x-axis is 2 times I minus 1 over n. You have the parabola looking like this. This height, this is f of 2i minus 1 over n. The base is 2 over n. So the area of this rectangle is the height times the base. You evaluate f at 2i minus 1 over n times the base, which is 2 over n. And of course, the function is x squared. So this is 2i minus 1 over n all squared times 2 over n. So this is 4i minus 1 squared times 2, that makes 8. I minus 1 squared over 2, n squared times n over n cubed. So each of these rectangles has an area 8 over n cubed times I squared, I minus 1 squared, or 8 over n cubed, I squared minus 2i plus 1. So that's the area of one of these red rectangles. And so the area under the parabola is approximately the sum of the areas of each of these n rectangles. So this is the sum, I goes from 1 up to n, of this expression, 8 over n cubed, I squared minus 2i plus 1. I can factor the 8 over n cubed out of this. 8 over n cubed, summation, I goes from 1 up to n, I squared minus 2i plus 1. Of course, we have to evaluate this. And I can actually write this as 3 separate sums. So let me do this. This is 8 over n cubed. Summation I goes from 1 up to n, I squared, minus 2 times summation I goes from 1 up to n, I, plus summation I goes from 1 up to n, 1. And we need to know what these sums are. So let's take a look at that. The easiest one is summation I goes from 1 up to n, 1. This just means as I goes from 1 up to n, you just add 1. 1 plus 1 plus 1 plus 1. You have n terms. And if you add n to itself n times, you get n. The second term is summation I goes from 1 up to n, I. That means 1 plus 2 plus 3, n minus 2, n minus 1 up to n. It's the sum of the first n integers. And you can figure out a formula for that, because you can notice that if you take the smallest term and the largest term, 1 and n, they add up to n plus 1. And if you take the next smallest and then the next but largest one, 2 and n minus 1, they also add up to n plus 1. And if you take the third term from below and the third term from above, n minus 2 plus 3, they add up to n plus 1. So if you just sort of like look at this as kind of like an onion, you sort of like peeling it, or you have like the first and the last terms, you have these successive terms, and they all add up to n plus 1. That is, every sum of two terms in this way adds up to n plus 1. You have n terms altogether, so you have n over 2 pairs, and each pair adds up to n plus 1. So you get this formula for the sum of the first n integers. It's n times n plus 1 over 2. And there's also a formula for the sum of the first n squares. 1 squared plus 2 squared plus 3 squared up to n squared. Or 1 plus 4 plus 9 up to n squared. This is a little bit more complicated, but there's a formula for it, which is n times n plus 1 times 2n plus 1 over 6. So we have explicit expressions for the sum of n of 1 n times, the sum of the first n consecutive numbers, and the sum of the first n consecutive squares. So let's go back to the previous page where we had an area approximation. That is, we had that for the parabola. This area was approximately 8 over n cubed times summation I squared from 1 to n minus 2i from 1 to n plus summation 1, sum from 1 up to n. And now I know what each of these terms is. This is 8 over n cubed. Sum of the I squares, that's this. n plus 1, 2n plus 1 over 6. Minus 2 times the sum of the first n integers. That's n plus 1 over 2 plus n. So that's what we get. Now, you have to know algebra to do calculus. So let's see what this is. This is 8 over n cubed. These twos cancel. So I have 1/6. If I multiply this out, I get 2n cubed plus 3n squared plus n minus n squared minus n plus n. These cancel, of course. Let's see, what do I have here? I have 8 times 2 is 16 over 6, and the n cubes cancel. So from this first term, I get 8/3. From the next term, I get plus 24 over n plus n over n squared minus 8 over n. So this looks like 8/3 plus 16 over n plus 8 over n squared. Let's see. Let me just check the arithmetic because I don't think this is quite right. So It's 8 over n cubed times n plus 1 times 2n plus 1 over 6 minus 2 times this plus n. So that's completely correct. This is n 2n cubed plus 3n squared plus n over 6 minus n squared minus n plus n. So this is 4/3. No, this is 8/3 plus I have 24 over n plus 24 over n plus 8 over n squared minus 8 over n minus n plus n. This 8/3 plus 16 over n oh, sorry, there's a 6 here. This is 24 over 6. So that's 4 over n plus 8 over 6 plus 4/3 n squared minus 8 over n. So it's 8/3 plus 4n, 4 over n. Oops, there a minus sign? Let's just see. Yeah, 4n minus 8n, minus 4 over n plus 4/3. Okay, so the details of the arithmetic, this is correct, but the important thing is now just to see what this final result was, to understand what's going on. So here we have the parabola, y equals x squared from 0 to 2. And we divide this interval from 0 to 2 into n equal intervals. And we construct in each of the subintervals a rectangle. And the sum of the areas of the rectangles is equal to 8/3 minus 4 over n plus 4/3 1 over n squared. That's when you have n subdivisions. And that's an approximation to the area. And we can say that the area should be the limit as n goes to infinity of this sum of the areas, which is what is called a Riemann sum. That's the limit as n goes to infinity of 8/3 minus 4 over n plus 4 over 3n squared. And as n goes to infinity, these two terms go to 0, and we just get 8/3. So this is a geometrical argument that the area under the parabola should be equal to exactly 8/3. And that's what it is. And one extends this to give have a general idea of how to find the area under some reason. So if you have some curve y equals f of x, and we want to find the area, and suppose this curve is greater than or equal to 0. So the graph lies above the x-axis for x between a and b. So whatever the function looks like, it can be very complicated. This is A, this is B. And here we have the graph of y equal f of x. And we want to find the area under the curve. So divide the interval AB into n subintervals. They don't have to be the same length, but if they are, it's sometimes easier. So let's say A is x0, and then there's x1, x2, xi minus 1, xi up to b, which is equal to xn. And here's some subinterval. In each subinterval, choose a point C sub I. So C sub I is between xi minus 1 and xi. And consider the rectangle with base the interval from xi minus 1 to xi, and height f evaluated as C sub I. So here is the picture. Here's xi minus 1, and here's xi. And we have the curve, y equals f of x. Choose some point C sub I in this interval. It could be an endpoint, but it doesn't have to be. So if you draw the perpendicular here, this point has coordinates C sub I, f of C sub I, and draw the horizontal line through that. So I've cut out a rectangle. The area of a rectangle is the base times the height. So the area of the rectangle is, suppose I just use the notation delta x sub I is xi minus x sub I minus 1, just this length. So height times the base, f of C sub I, delta x sub I. That's the area of this red rectangle. And I do that for each of the subintervals from A to B, and I have n of them. So I sum this up as I goes from 1 up to n. And this is approximately the area. And the idea is if your function f is nice, in some sense, reasonable, the limit as n goes to infinity will exist. And this will be exactly the area under the curve from A to B. So on the interval from A to B. And we call this the definite integral. And the notation is this integral sign, f of x dx, but we put a here and b here. A on the bottom of the integration sign and b on the top. And this means the area under the curve from A to B. And another name for that is area. Now, you'll notice so we have that the definite integral, the integral from A to B of f of x dx, this is a limit as n goes to infinity of expressions that look like f of C sub I delta x sub I. And what this means is we have for each n a partition of the interval from A to B, and in each subinterval of consecutive points of subdivision, we pick some c sub I and f of c sub I. Now, it could be that the graph of your function looks like this. So there's certain values where the function is negative. In that case, f of c sub I is negative. And so there's a more sophisticated understanding of the definite integral for a function that could be positive or negative. So if this, for example, were the graph of the function, this is A and this is B, we have part of the curve is above the x-axis, and part of the curve is below the x-axis. And what the definite integral really gives us is the area above the x-axis minus the area below the x-axis. So you could have a definite integral which is negative, and that just means there's more area below the x-axis than there is above the x-axis. So just as you have positive and negative numbers, you have positive and negative area. You know, a positive number is a number to the right of 0 and a negative number is to the left. A positive area is an area above the x-axis and a negative area is an area below the x-axis. That's all it is. So, and if we write this down exactly, this is, well, that's what it is exactly. That's the definite integral. Now, if you think of it like this, some things that look very complicated actually turn out to be not so hard. So suppose we had a problem which mathematically was stated like this. Compute the integral from -2 to 2 of the square root of 4 minus x squared dx. So what this means is, if you look at the graph of the function y equals the square root of 4 minus x squared, you graph that, and this is the area under the curve from -2 to 2. Now, if you look at this, you might say, well, I'll get rid of the square root sign by squaring both sides.
So we cannot see.
You can say, I'll get rid of the square root sign by squaring both sides. So this is the same as the equation x squared plus y squared equals 4, which is 2 squared. And that you recognize as just the equation of the circle, radius 2. Square root of x is the positive part of that. So this is just asking for the area of the semicircle centered at the origin with radius 2. For the whole circle, it was pi times the radius squared. That's 2 squared. But this is half of the circle, so it's half of that. So this is equal to 2 pi. So just understanding that the integral, definite integral means area under a curve, you can sometimes compute the areas quickly. Here's another example. Suppose we were given the following problem. Compute the integral from 0 to 3 of x plus 2 dx. So how do we interpret that? We have the function y equals f of x equals x plus 2. What does the graph look like? This is a straight line with y-intercept 2 and slope 3. So this is the equation of this this is the graph of this function. And we're asking for the integral from 0 to 3. That means this area, the area under the curve. So this is the area. What is this? This is a trapezoid. And you know the area of a trapezoid is the average of the right and left hand vertical sides times the base. This is 2 and this is 5, so you get 2 plus 5 over 2 times 3, which is 21 over 2. So you know the area of a trapezoid, that's what this integral is. If you just had a constant function, like the integral from 1 to 3 of 4 dx, here you're looking at the function y equals f of x equals to 4. That's just a horizontal line. So from 1 to 3, that's in this region, and the function is just y equals 4. That's just a rectangle. This is equal to the area of the green rectangle. That's the base times the height, which is 8. Okay. Questions about this? Okay, well, it seems like it's very hard to actually calculate these integrals because they give you an area, but except for simple things like rectangles, trapezoids, and circles, you don't know what the area is. But in a minute, I will explain how to find all the areas. That's pretty good. But I do want to just mention some properties of definite integrals. So the two simplest properties are the following. If I have the integral from a to b of some constant k times a function f of x, I can take the k outside. That's k times the integral from a to b of f of x. And if I have the integral from a to b of the sum of two functions or the difference of two functions, that's equal to the sum or difference of the integrals. So these are two properties that you might easily use without thinking much about it. And now you know that it works. So here's an example of this. It's very instructive. Suppose we're given some information that the integral from 1 to 3 of x squared dx is equal to 26 over 3. These are all true statements. The integral from 1 to 3 of x dx is equal to 4, and the integral from 1 to 3 of 1 dx is equal to 2. But suppose you had to calculate the integral from 1 to 3 of minus x squared plus 4x minus 3 dx. So we use the fact that the integral of a sum or difference is the sum of or difference of the integrals. So this is the integral from 1 to 3 of minus x squared dx plus the integral from 1 to 3 of 4x dx minus the integral from 1 to 3 of 3 dx. So I could take this minus sign outside. This is minus the integral from 1 to 3 of x squared dx. Take the 4 outside. 4 times the integral from 1 to 3 of x dx minus 3 times the integral from 1 to 3 of just 1 dx. And I know what these integrals are. So this is minus 26 over 3 plus 4 times 4 minus 3 times 2. So that's minus 26 over 3. 16 minus 6 is 10 plus 10. So that, if you do the arithmetic, is 4/3. So using those two simple properties of integration, we can calculate something like this.
So,
Yeah. Question?
yes, I don't get. Did you switch like x by 3?
I don't know what you mean by switch. So we're integrating from 1 to 3. So we're given, as a start, some information. We're given that this is true. The integral from 1 to 3 of x squared is 26 over 3. We're given that the integral from 1 to 3 of x is 4, and the integral from 1 to 3 of the constant function 1 is 2. So these are given. And now we have the following problem. Calculate this integral. So we use the fact that the integral of a sum or difference of functions is the sum or difference of the integrals. So this is the integral of minus x squared plus the integral of 4x
Got it.
minus the integral of 3. And I can take the minus sign outside, the 4 outside, the minus 3 outside. And I know what this is. It's that. And this is this. And this is this. So I just plug in those values. Minus 26 over 3 plus 4 times 4 minus 3 times 2. And that's the answer. Let me just state two other properties of integrals that have to do with inequalities. If f of x is greater than or equal to 0 for x between a and b, then the integral from a to b of f of x dx is greater than or equal to 0. And the reason is that from a to b, the function's non-negative. It's always above the x-axis. So the area under the curve has to be positive. It can't be negative. That's what this means. And a similar statement is that if f of x is less than or equal to g of x on the interval from a to b, then the integral of f of x is going from a to b is going to be less than or equal to the integral from a to b of g of x dx. So these are some simple facts. Now, none of this tells us how to actually calculate the area under a curve or how to calculate equivalently the definite integral. And for that, we use the fundamental theorem of calculus. And what that says is the following. let capital F of x be the antiderivative of the function little f of x. So that means that if you write this in terms of integrals, the indefinite integral of f of x dx is capital F of x. Then, if I want to calculate the definite integral from a to b of f of x dx, this is going to equal capital F of b minus capital F of a. So this is the amazing formula that relates an area under a curve to an antiderivative of a function. And this is the fundamental theorem of calculus. And at some point I might sketch a proof of this, but the important thing is to know the statement and how to use it. So let's look at an example. Suppose I have f of x equals x squared. And I want to find the area under the curve between 1 and 2, between 1 and 3. So here is the parabola, and I want to find the area from 1 to 3. So the area under this parabola, this is just notation, the integral from 1 to 3 of x squared dx. Well, we have to ask, capital F of x is the antiderivative of x squared. Well, we know the antiderivative of any power of x is 1/3 x cubed plus a constant. That's the antiderivative. So this is going to be f of 3, capital F of 3, minus capital F of 1. That's equal to 1/3 3 cubed plus c minus 1/3 1 cubed plus c. You'll notice the plus c and the minus c cancel, so we can ignore the constants here. And we just get 1/3 3 cubed minus 1/3 1 cubed. That's 27/3 minus 1/3 is 26/3, which was what was given to us in the last problem. This is an example of the use of the fundamental theorem of calculus. So it reduces computing a definite integral to computing an indefinite integral. Of course, if you can't compute the indefinite integral, you're out of luck, but hopefully in every problem you get, you'll be able to compute the indefinite integral. Let's see. Here's another problem we had mentioned earlier. Suppose I take y equals 4 minus x squared on the interval from -2 to 2. So we're looking at this parabola. And the question is, what is the area under that curve? So that area is equal to the integral from -2 to +2 of the function 4 minus x squared. So this function, let me write it as f of x equals 4 minus x squared. Capital F of x is the antiderivative. And you should have done enough homework problems by now that you can tell me very quickly what is the antiderivative. What is the antiderivative of 4?
4x.
4x. And what is the antiderivative of x squared?
1/3 x to the power 3.
Exactly. 1/3 x to the power 3. That's f of x. So this is going to be capital F of 2 minus capital F of -2. So what are these numbers? F of 2 is 4 times 2 minus 1/3 times 2 cubed. That's 8 minus 8/3 is 16/3. And f of minus 2 is 4 times minus 2 minus 1/3 times minus 2 cubed. That's minus 8 plus 8/3 minus 16/3. So this is 16/3 minus minus 16/3. Minus times minus is plus, that's 32/3. So the area under the parabola is 32/3. Right? I mean, that's pretty good, because until an hour ago, it would have been impossible for you to do this. The Greeks could never do this. No one could do this until the invention of calculus. So this is really quite useful. Let's do some more examples. Suppose we have the integral from 1 to 4 of 3 times the square root of x dx. So we need to find the antiderivative of 3 times the square root of x. That is, capital F of x will be the antiderivative of 3 root x. I can take the 3 outside. I can write square root of x as x to the 1/2 dx. What is the antiderivative or the integral of x to the 1/2? Can someone figure that out? So the rule is always the derivative of x to the n dx, so long as n is not minus 1, is 1 over n plus 1, x to the n plus 1. And here, this exponent is a half. So this is 3 times 1 over a half plus 1, x to the half plus 1. I don't want to forget the constant. So what is this? This is 3 times 1 over a half plus 1 is 3 halves, x to the 3 halves.
Half.
So this is 2 x to the 3 halves. And you can check, if you differentiate 2x to the 3 halves, you get 3x to the 1/2. But this is the antiderivative. That's my f of x. So this is going to be capital F of 2 my f of 4 minus capital F of 1. That's 2 times 4 to the 3 halves minus 2 times 1 to the 3 halves. 4 is 2 squared. 2 to the 3 halves is 2 cubed. That's 8. So this is 2 times 8 minus 2 times 1. That's equal to 14. So for this function, 3 root x, the area under that curve is equal to 14. Suppose we want to find the integral from 1 to 7 of 6x squared plus 2x minus 3 dx. So this is going to equal capital F of 4 minus capital F of 7 minus capital F of 1, where this function capital F of x is the antiderivative of 6x squared plus 2x minus 3 dx. So calculate this integral and then plug in here to find the answer. And I'll give you a minute or two to do that. But what is this integral? What is this equal to? What is this function capital F?
It is 2x to the power 3 plus x squared minus 3x plus c.
Oh, right, but we don't need to see here. Right, because if you differentiate this, you get 6x squared plus 2x minus 3. So what is capital F at 1 equal to? It's 2 times 1 cubed plus 1 squared minus 3 times 1. 2 plus 1, this is 2, plus 1 minus 3 is 0. What is capital F of 7? That's 2 times 7 cubed plus 7 squared minus 3 times 7. What is 7 cubed?
$343.
Yep. So it's 2 times 343. 7 squared is 49. 3 times 7 is 21. So this is 686. And see, 49 minus 21, that's minus 48. So this looks like it's 638. So this is equal to, if this is correct, you just have to check the numbers. 638 minus 0. 638.
Professor?
Yeah.
You said 49 minus 21 is minus 48.
Oh, sorry. Thank you. It's minus 28. Oh, sorry. 49 minus 21 is plus 28. So this makes this 714, I think. Yeah. Okay. Suppose we have the following problem. Suppose we have the function f of x equals 1 over x. So that decays like that. And suppose we want to find this area under the curve from 1 to 3. So the area is the integral from 1 to 3, 1 over x dx. If you have the indefinite integral of 1 over x dx, what's the antiderivative, or the definite integral? It's log x. So this is log 3 minus log 1. Log 1 is 0. So this is just log 3. That's the area under the curve. Suppose we have the function f of x equals the absolute value of x, and we want the integral from minus 1 to 2 of f of x dx. So we have to be a little bit clever here, because the absolute value of x is a slightly complicated function. See, what does the graph of the absolute value of x look like? It's y equals x for x positive and y equals y minus x for x negative. So if we want the integral of f of x dx, or the integral from minus 1 to 2 of the absolute value of x dx, it's the area under the curve here and here. Actually, in that case, we can just do it by elementary school geometry. This is a right triangle. The sides are 1, so this has area a half. And this is another right triangle. The base is 2, the height is 2. So the area is 4 over 2, or 2. And the sum is the area under this curve. So this is just 3 halves. Sorry, 2 plus 1. This is 5 halves. That's what the answer is.
Well, can we do it another way?
Yes.
Right, Angela, yes.
So you can do it like this. You can say the integral from minus 1 to 2 of the absolute value of x. You see, the absolute value of x is defined like this. It's equal to x if x is greater than or equal to 0, and it's minus x if x is less than or equal to 0. So it has 2 different ways of being written depending on whether x is positive or negative. So I can divide this up into 2 pieces. This is the integral from minus 1 to 0 of x dx, plus the integral from 0 to 2 of the absolute value of x dx. And if x is from minus 1 to 0, here x is negative. So the absolute value of x is minus x dx. And for x between 0 and 2, the absolute value of x is just equal to x. So I could write it like this, and I know that the antiderivative of x dx is a half x squared. So this is equal to minus f of 0 minus f of minus 1.
I cannot see.
Right? So if I break the integral up into 2 integrals, because I'm dividing the interval from minus 1 to 2 into 2 pieces, the piece where x is positive and the piece where x is negative, I get this. And this integral is f of 2 minus f of 0. So an f of x is a half x squared. So this is minus 0 minus a half. And this is plus 2 minus 0. So I get a half plus 2, or 5 halves. So I mean, there's only one answer. The area is whatever it is, and I get the same answer both ways. But breaking it up like this is an interesting technique, and sometimes you need to, well, It can be used in other situations, such as the following problem, which is an example in the text. This is example 2 in section 5.4. We want the integral from 0 to 2 of the absolute value of 2x minus 1 dx. So this is a little bit more complicated. You know that the absolute value of 2x minus 1 is going to be 2x minus 1 if 2x minus 1 is positive, and it's going to be minus 2x minus 1 if 2x minus 1 is negative. That's just the definition of absolute value. Absolute value of a number is equal to the number if the number is greater than or equal to 0, and it's minus the number if the number is negative. So this is the same as this function is equal to 2x minus 1. To say 2x minus 1 is greater than or equal to 0 means x is greater than or equal to a half. And minus 2x minus 1 is 1 minus 2x. And that's true if you solve this inequality if x is less than or equal to a half. So if we graph this function, zero, 2, 1/2. If x is greater than or equal to a half, this is the function. Well, let's see, if x is less than or equal to a half, it's 1 minus 2x. So.
Sorry, can you move it down just a little bit?
Yeah. So this is the line x equal to a half. If x is less than or equal to a half, this is the function 1 minus 2x. Looks like this. And for x greater than or equal to a half, it's 2x minus 1. So it goes up like this. When x is equal to 2, this is 3. So this is the graph of the function. And the area under the curve is this. And again, we can do it by high school geometry. This is a half and this is 1. So what is this area? For this triangle, it's a half, the base, times the height, plus for this triangle, it's a half, the base is 3/2, and the height is 3. So that's 1/4 plus 9/4 is 10/4 or 5/2. So just doing this by looking at these triangles, we get the answer. But we can also do it as we did the previous problem. We can write this as a sum of the integral from 0 to a half plus the sum from 1/2 to 2. From 0 to a half, this is negative. So this is equal to minus the integral from 0 to a half, 2x minus 1 dx, plus the integral from a half to 2 of 2x minus 1 dx. Now, if we take the function capital F of x to be the antiderivative of 2x minus 1 dx, that's just x squared minus x. So this is minus, for this function, f of a half minus f of 0 plus f of 2 minus f of a half. For this function, f of a half is a half squared minus a half. That's a fourth minus a half, or minus a fourth. F of 0 is 0. And f of 2 is 2 squared minus 2 is 2. So we get minus a fourth plus f of 2 minus f of a half minus a fourth. So that's a fourth plus 2 plus a fourth. That's 2.5 or 5/2. So that works out by itself. Okay. Any questions about this? We covered quite a bit today, but this work involving the fundamental theorem of calculus is really very important. Well, obviously, because that's the name of the theorem. It's fundamental. And I would really encourage, we only have 3 more classes, and it really is important to learn about the integral in Math 175. It comes at the end, but it's extremely important. So I would really encourage you to spend as much time this weekend doing problems involving integrals. Even work ahead a little bit if you can. And on Monday, the best thing is if you have some problems that are hard, that you have some questions about. Either you did them, but you still are unsure about something, or you couldn't do them. But in any case, that's really the best thing. Okay. Anything else before we go? So one other thing you should do, I will, the final exam's not for a few weeks, but there's a practice final exam that I will email out to you. You can actually download it from the math department website, but I'll also email it out to you. And it's good to be working on the practice exam, which covers the whole semester. And the last class will be devoted to just going over the practice exam. But you really should try to do as much of it as possible on your own. Okay, well, if there are no questions, then we will stop right here. Bye all.